Alright, so today we're talking about polynomial functions. The goal today, very simple and short and sweet. You will be able to graph polynomial functions. This is without a calculator. Okay? This is without a calculator. Shifting into this new unit, deal more with these different types of polynomial functions. Okay? You have your base, parent functions, and things like that. We're getting more into the complex types of functions here. Okay? So, your polynomial functions. Some of this will be a review because from doing that activity, we'll go back over some of that information. Some of this may be new. So here we go. The graph, a polynomial function of n degree is a function in the form of what you see here, where n is a non-negative integer and a not, a sub 1, a sub 2, so on and so forth, are real numbers with a sub n not equaling 0. So in other words, every polynomial function is set up like such, okay? Every polynomial function is set up like this, where these here are real numbers, like 2, -6, 100, so on and so forth, okay? You have your variable x, and then you have your exponent. N is a real number, okay? So whatever n is, it is decreasing all the way to when we have no x's, okay? So if n was 5, this will be x to the 5th, x to the 4th, x to the 3rd, x to the 2, so on and so forth, all the way down to where there be no x's, just your constant, okay? One thing you need to make sure of, as we saw in number 6, is that you need to make sure that it's in order, so that way you can identify your appropriate and correct in behavior, okay? Now, the leading coefficient of a polynomial function is the coefficient of the variable with the greatest exponent, okay? So whatever the largest exponent is, the number attached to it is the leading coefficient, okay? So if you look at number 6 from that activity, what's your leading coefficient? It would have been -2, because your largest degree is what? It's a 6, okay? So even though it wasn't in basically standard form where all your exponents were decreasing, your largest exponent is 6, which means the number attached to it is your leading coefficient, okay? And before we go a little bit deeper into that, we're just going to review the rules of transformations real quick, okay? Because they do apply to some monomial functions, all right? So, you have x minus 2 to the 5th, and you have negative x to the 4th plus 1. Now, using what we know about n behavior, our degree is even or odd? Odd. And our a, our number in front, is positive or negative? Positive. So show me with your arms what this would look like if I were like to go into my calculator and graph it specifically. Okay? And remember, pretend like I'm looking in the same direction you guys are. Okay? Very good. Yes, it should look like this. Okay? With the right side going up and the left side going down. Okay? Fifth power polynomials look very similar to cubics. Okay? But that -2 means what? You go to the right too, because it's on the inside with the x. Anything on the outside affects your y's, anything on the inside affects your x's. So everything gets moved over 2 units, and you have your function. Okay? Over here we have an x to the 4th, negative x to the 4th plus 1. This is a quartic, okay? Your most basic quartics do look very similar to a quadratic, okay? Your most basic quartics, okay? I'm talking about like your monomial ones. What does that negative do to that function? What does it do? Flips it upside down, so that means it gets flipped, it gets reflected over the x-axis, and what does that plus 1 mean? It means it goes up. And so then we have that. So the same rules still apply for transformations, and that's a little quick review of Unit 1. Okay? Questions? So going back to last time. So the leading term test uses the power and coefficient of this term to determine a polynomial's end behavior. That's what you guys did in that little investigation activity. That's what we talked about right before we started this lesson. So here are the general rules, okay? When it is odd and A is positive, A being that leading coefficient, it's going to shoot up to the right, shoot down to the left. The squiggly basically means that there's something else happening, okay, in between your end behaviors, okay?
So it could be like going up and then all of a sudden this jerk and all of a sudden go back down.
Exactly. So the squiggly basically means there might be some extrema going on, okay? You might have some x-intercepts, some y-intercepts, so on and so forth, but no matter what, the ends are going to look like this, okay? And today's lesson is basically getting you some experience with graphing what exactly is happening in that squiggly part, okay? So here's your general makeup. For those who might have struggled on the activity or didn't do the activity. Alright, so, we good? Are we still good? So, I want you guys to take a second. If you're watching this video, pause the video and describe the end behavior using limits, okay? And I want you to justify your answer, so tell me why. You can do it in a quick sketch of what the function would look like. We're not graphing these, we're using our knowledge of end behavior, leading coefficient, and degrees, okay? It's like what you did on that activity on the back side, all right? Here we go. So, show me with your arms what this one looks like. Remember, show it like, I'm not looking at you. What will it look like? Very good. Because it is even and A is positive. So because our exponent is even and our leading coefficient is positive, that means it's going to open up. Something's going to happen in between here. So the limit as x approaches positive infinity is infinity. And the limit as x approaches negative infinity is infinity. Show me with your arms, what does B look like? Majority, by the majority have it, okay? What is the degree? It is odd. And is my leading coefficient positive or negative? It is negative, it's right here, okay? So make sure you're looking at the entire polynomial. So then, the right end behavior is going to be what? What's the right end behavior? It goes to negative infinity. So basically what's happening on the right side of it is going to negative infinity. What's the left end behavior? Positive. So it is positive. Show me which arm will the C look like. Very good. So, because N is odd and A is positive, so what's my right end behavior? Infinity. And what's my left end behavior? Negative infinity. Questions? Good stuff. All right. Maximum and minimum. We talked about this already with extrema. Are located at turning points. Okay, so that maximum point, that minimum point, they are called turning points. And a polynomial function of n has at most n distinct real zeros. And it has at most n minus 1 turning points. That means we can have up to that many zeros and up to n minus 1 turning points. Okay? What's another word for zeros? Roots or x-intercept. So basically, whatever the degree is tells us that we could have possibly that many x-intercepts and at most n minus 1 turning points. So when we look at this problem here, what is our degree of this polynomial? It is what? It is 3. It's the largest one. So that means we have how many possible zeros?
2.
Careful. 3. But what is the 3? What does the 3 minus 1 represent? The turning point. So we have at most 2 turning points. So that means we have at most 2 extrema. Okay. Now we could have less than that. We could have more, or we could have less than that, but we could have no more than 2 turning points.
Oh, okay.
So now we're going to determine the real number of real zeros, okay? Because maybe not all of them are going to be real. There might be some imaginary ones, okay? We want to find out the real ones. How do you find an x-intercept? A good review of Unit 1.
Plug in 0 for y.
You equal the function to 0. So that means you plug in 0 for y. Now these are the easier problems of finding your real zeros, okay? We'll get to the harder ones next week. So, how do I solve for x?
Factor out an x.
Factor out an x. So I'm left with x squared minus 5x plus 6. And then what I do to the inside? Factor. Factor this. What two numbers multiply to give you 6 that add to give you negative 5?
Negative 6 plus 1.
Okay. Is it 6 and 1 or is it 2 and 3?
Oh,
It's negative 2, negative 3. Because when I multiply them, I get a positive 6. And if I use 1 and negative 6, I'll get a negative 6 when I multiply. So be very careful. Now I have to apply a property to solve for x. What property? What's the name of the property? 0. Doesn't work. This 0 product property. So 0 product property. So you said both of your factors equal to 0. Not both, all. Sorry. And you solve for x. Okay? You already have one of your zeros here. And your other one is x equals 2. And your last one is x equals 3. So you had a possible 3 real zeros, and they actually all are real. Huh? Well, it's always good to check. But one thing I will say is this: say this is a question on the test, and you have some time to finish the test. I would plug in these values and make sure that you did get 0. Plug into the original, make sure you got 0. Because say you use positive 1 and negative 6 when you factor. Well, when you solve it out and you get your x's, when you plug it back in, it would definitely show you that those were not the zeros, and you need to go back. So I would say, if you take your time, you're good. But it's always good to check. Always check for the radical ones. Look at this one. What's my degree? 4. So I have at most how many possible zeros? Possible real zeros, sorry. 4. How many turning points? 3. Remember, it's always n minus 1 for your turning points. So now let's find the real ones. This was different from the other one. There's no GCF. But how could I solve this? I know I have to set this equal to 0. Because I'm looking for my x-intercept. This is my zeros. So how do I find my x's? Sure.
Say you can split it into two separate.
I think I might be on something else.
You should make it like 2 quadratics.
What do you mean? Tell me out.
Like just like what he was trying to say.
Okay.
Not
Like you said,
quadratics, but like you just split them into like I couldn't find the word for it. So like you'd make this one x to the 4th, and then make the other one like 3x to the 4th.
Well, we couldn't split it that way. We couldn't split it that way. Huh?
that's what I'm.
Not necessarily for this one. This is still one of the easier ones. P over Q is next week.
That's a long one.
This is a long one. These are your more simple polynomial functions. We'll get to your more not so simple polynomial functions. Yes.
We put 4 on the other side and then.
We wouldn't be able to do that. I mean, we would get a solution, but it wouldn't be the correct solution. Yes.
I know this is probably wrong, but wouldn't you put two functions or something and like
like tell me if you want.
You have two functions and then like you plug in x for like this, it's like the complementary or something like that. It's probably wrong, but
I could explain this kind of using what you're saying. I could definitely use what you're saying to solve this problem and to explain it.
You can just factor this, can't you?
You can't factor this.
How do you subtract?
It's x squared plus something.
Normally when we factor, right, our degree is a 2 here. So like it would be x squared minus 3x minus 4. This is just a higher order quadratic, okay? So instead of putting x in x here, we're going to put x squared instead. Because think about it, if we were to FOIL this, wouldn't it give us x to the 4th? And no matter what our inner and outer terms would be, they would have an x squared at the end for the middle. Alright? And it works if it was x to the 6th and x to the 3rd, x to the 8th, x to the 4th. It would just continue to increase the power of the exponent inside of the parentheses. Okay? So, what two numbers multiply to give you -4 that add to give you -3? -4 and +1. And so then we can solve it the same way.
excuse me, teacher.
So, then we continue to solve it like normal. We set both equal to 0. And solve. Add 4. Then what? And whenever you square root an equation, you always get plus or minus. So there are 2 of your zeros, +2 and -2. Over here, we have to subtract 1, and then what? Radical, square root. What do we get here?
Two imaginary numbers.
2 imaginary numbers, okay? So we get no real zeros here. We would get 2 imaginary. So here's an example where you had a total of 4 possible real zeros, but only 2 of them were actually real. The other 2, which were imaginary, would not be plotted on a real coordinate plane, your classic x and y axis. Okay? If you had a complex coordinate plane, that's for another year, probably college.
I'm not taking
Last little bit. If a factor x minus c occurs more than once, then it is called a repeated 0. In quadratics, it's known as a double root, okay? However, for your higher power polynomials, it's called a repeated 0, but it's also known as multiplicity. Now, when a 0 has even multiplicity, the graph will be tangent to the x-axis at that point, and the value of f of x, also known as y, does not change signs. When a 0 has an odd multiplicity, the graph will cross the x-axis at that point, and the value of y will change signs. Okay? So we're going to talk about this a little bit more. What does it mean to be tangent? Christian? It touches it. Does it cross it? No. So in this case, when a 0 has even multiplicity, the graph will touch the x-axis. Okay? And the y values will not change signs. So basically, your curve is going to get close to the x-axis, touch it, and then like ricochet off. Okay? That's what it would look like. And of course, it can go on the other side. However, if it has an odd multiplicity, the graph will cross the x-axis. And the y's will change signs, like it does here. Okay? Now by multiplicity, again, that means if a 0 occurs more than once. So say you have this problem, you factor it out, and you're solving it down. And you end up getting x equals 1 and x equals 1 again. Well, that's an example of when you would have even multiplicity, because x equals 1 shows up 2 times.
But it's an odd number.
Even though it's an odd number, the fact that it shows up twice means that it has even multiplicity, or a multiplicity of 2.
So how could one show up 3 times?
How one, depending on the polynomial, it definitely would have to be like a higher order degree, like to the 4th or to the 5th power. So that maybe when you work it out, it end up being like x minus 1 to the third power, that would be an example when it would show up more than twice.
Okay.
You'll see. Are there any other questions? So let's go here. State the number of possible zeros and turning points. We should be able to do this, right? You've got 30 seconds. How many possible zeros will I have?
4.
I'll have 4 possible real zeros. How many turning points? 3. And how'd you figure that out again? And what is n? 4 is the largest degree, okay? So now we're gonna find the real zeros. Look at this problem. Again, this is still one of the easier ones, okay? We'll save the more complex ones for next week. What do you notice? There's a negative. Caleb?
You can factor out x squared.
I can factor out an x squared. Because both of them have an x squared in common. Now I got a question, a follow-up question to this. My first term is negative. So could I factor out a negative x squared?
Yeah.
You actually can. And I mean, for me personally, sometimes negatives trip me up. But, so it may trip you up too. So why not make it a little bit easier on yourself by factoring out a negative, so that way on the inside, you'll have a what? A positive x squared instead of a negative one. And then I would have what after that? Plus x minus 2.
Oh, that's cool.
So when I take out a negative, it basically allows me to have a positive x squared on the inside instead of the negative. So that way when I factor, I don't have to worry about a negative anywhere. Does that make sense? Okay. So let's factor this. So, here are your zeros. Now realize, x equals 1. It only showed up one time, correct? That means it had a multiplicity of 1. It only showed up one time. Over here, x equals negative 2. It had a multiplicity of 1. Now, it didn't say nothing about this in the problem, in the directions. I know this, but I want to go back over this concept before we get to the next example. However, over here, at 0, if we actually had worked this out,
Okay.
negative x squared equals 0. We would have had to divide by a negative 1, which will still give us 0. And when we take the square root, we always get what normally? Plus or minus. Now realize 0 can't have a plus or minus because it's neither negative or positive. But the truth of the matter is that 0 is a double root. It is a repeated 0. Technically, you have the positive version and then the negative version. For those who are watching the video, I'm doing imaginary quotation marks right now, okay? So 0 actually has a multiplicity of 2, which means that if we were to graph this, it would not hit 0. What does it mean to have an even multiplicity? It touches 0. Whereas at negative 2 and at positive 1, it would cross through. Okay? So that's, and we want to make sure that we identify that so that way if we ever had to graph this, we would know. Okay? So,
Is that why it just goes up, touches it, and kind of goes around it?
no, so let's do like a quick sketch of this. Okay? It's even. A is negative. Show me with your arms what it should look like. Okay. So then that means it should look like this. My end behavior should look like this, right? So at negative 2, it's going to cross. It's going to do something up here. At 0, it's going to touch. My y's are not going to change. And then it's going to cross at 1. Did everybody see that?
Yeah, that makes more sense. Wait, so
Do it again. Okay, so we know our end behavior is going to be this, because it's negative and it's even. So that means my graph is going to cross at -2. It's going to touch at 0, but not cross. And then it's going to cross at 1. So it does follow our end
Is
behavior.
that kind of like how you would like you use the zeros to graph it?
Use the multiplicity as well. And then even a few extra additional points. And then we know that it should both point down because it is even and it's a negative. So we use that in behavior as well. So we're going to put it all together. We're actually going to do that right now. Okay? So we're going to describe our end behavior, determine the zeros, state the multiplicity, find a few additional points so we get a really, really good graph, and then actually graph the function. Okay? So, and all of this, yes, it's going to be without your calculator. So here we go. Determine the zeros. Nope, I skipped one. Determine the end behavior. What's my degree here?
Four.
It's going to be 4. You have an x here, you have an x here, and then you have an x squared here. So an x, and an x squared total make an x to the 4th. Okay? So n is 4, and is a positive? Is a positive? Yes, it is. Because you have a positive 1, a positive 2, and a positive 1 that can multiply together. Like if I boiled out that end part, multiplied it by 2x plus 3, and then multiplied it by x, which I'm not going to do, but if I did it, you would have a degree of 4 and a positive x. Okay? So A is positive. So my end behavior will look like what? Show me with your arms what it would look like. If A is even, N is even, and A is positive. So that's what our graph should look like. So as x approaches positive infinity, it will be positive infinity. And as x approaches negative infinity, it will be positive. Now we have to determine the zeros. Our function is given to us in factor form, which is really nice. Which means that all we have to do is set every factor. What?
Wait, which part are we doing? I thought we were doing part B.
Yeah, that's part B. We're determining the zeros. So since it's already in factored form, we just set each factor equal to 0. So we have x equals 0, 2x plus 3 equals 0, and x minus 1 squared equals 0. Okay? So x equals 0 is one of our answers, one of our zeros. X equals -3/2 is another one of our zeros. And again, we get that by subtracting 3 divided by 2. What about over here?
You gotta do the FOIL.
This would be a tangent here. Okay? Because think about it. X minus 1 squared is the same thing as saying x minus 1 times x minus 1. So you would set both of those factors equal to 0. And you would get how many ones? 2. So 1 has a multiplicity of 2. Whereas -3/2 and 0 have a multiplicity of what? 1.
But if it's the square root of x squared, then it has a multiplicity of 2, right? No, square root of 0. I mean,
That's square root of 0.
square root of 0. Yeah,
Yeah,
sorry.
yeah. So here are our zeros. I know my end behavior should be like this. Well, pointing up. I know I should cross or touch is 0. Cross. At -3/2 I should. And at 1 I should touch. Okay? So now I'm just going to find a few additional points so I can get a really, really nice curve here. Okay? To To do that, let's pick a point in between our zeros. What's the point in between -3/2 and 0?
1.
-1. So to find the y coordinate when x is -1, you plug it in. Do this real fast without your calculator and tell me what y is. What did you guys get? You should get -4. So when x is -1, y is -4. So we know it comes from positive infinity, crosses at -3/2. It goes to -1, -4. It is coming to cross through 0. And if something happens, what's the point in between 0 and 1?
1/2.
1/2. Plug in 1/2 and give me a y value so I know exactly where we're plugging into the original function.
With like a calculator?
No, we're doing without.
No.
You can do it. I promise you're going to simplify me down to something really nice.
No, 2/4. 2/4. It's 2/4.
Which is a positive 1/2. You should have gotten 1/2 if you plugged it in, okay? And you really should do it without your calculator. Like I said, we're graphing this without a calculator, so you're going to be able to do these numbers without a calculator. So at 1/2, you're at 1/2, and it's going to touch 1, and then ricochet off. And there is your graph. You can do it. You can do it. Okay? I want you guys to try the next one on your own. Same directions and graph it. You can do it. I give you about 5 minutes. All right, so with your arms, what this looks like. Very good. So it's going to shoot up this way and shoot down this way.
But that's hardly a little ripple. Like, that's a big ripple.
It's a big ripple? Okay, well let's see. So our end behavior, as x approaches positive infinity, is going to negative. And as it approaches negative infinity, it goes to positive. Okay. What about my zeros? Did you factor out a negative x?
Yes.
Okay. You don't have to factor it out. You could have just factored out regular x, but then realize that be careful when you're factoring in here. So you get x minus 4, x plus 2.
Yes.
So your zeros should have been x equals 0
Yes.
for the one on the outside. X equals 4 for this one right here. And x equals -2 for this one right here. Yes? What was their multiplicity?
1, 1, 1, 1.
1, and 1. So that means that every single zero I'm going to
Go through.
go through. What points did you guys pick to graph this? 2,
-1, 3, and 1.
-1, maybe a 3. Okay, so I heard a few different ones.
1 and
Well, who plugged in -1? What you guys get?
2.
-5. Okay. When you plugged in 2,
16.
16.
so 3 is
15.
short.
That's why I plugged in 1.
What? Selected 1.
That's interesting. Let's double check.
Yeah.
Let's double check 2. When you plugged in 2,
You substitute check to 8. Then you get -8. 2 to the second power is 4, that's equal to 8. And 8 times 2 is 16. Combine that, you get 16.
okay.
Plus 8. Because
Okay, so plus 8. Yeah, plus 16. You get
Okay, so you get 16. Okay, so wait, where are my zeros? My zeros are at 0, -2, and 4. Okay, so that's why, because these are in between here. Okay, I get it. I'm thinking after 4 as well. Like it should have been negative somewhere after 4, right? Okay, so at -1, I'm at -5. At 2, I'm at 16, so I'm like all the way up here somewhere. And 3, I'm just a little bit below that. So coming from this positive infinity, I'm crossing, crossing again. Now, specifically, is that where the extrema is? No, I don't know for sure. I can definitely figure that out, but that's for another lesson. Okay? Well, honestly, what I'm trying to get is make sure that we understand our end behavior when I cross and when I touch the x-axis, and where my zeros are located. Are we good? Good stuff.